You're gonna do great. Yeah.
Hi, everyone. Thank you for joining DataCon LA 2021, and welcome to the Data Infrastructure and Security track. My name is Joanna Perdomo, your host, and our co-host today is Aaron Ortega, and together we'll be moderating the chat and the Q&A for you during the session. Today we have our guests, Davor, Bonaci, and Ryan Michael, and they'll be talking about overcoming data infrastructure limitations with a new paradigm for machine learning. Davor is co-founder and CEO of a Seattle-based startup, Kaskada. Previously, he served as the chair of the Apache Beam PMC and as a software engineer in Google Cloud since its early days and the inception of Cloud Dataflow. Ryan leads engineering at Kaskada, where he is pioneering a new way to think about feature engineering that enables flexible, data-dependent time travel without the possibility of temporal leakage. Before Kaskada, he served as a principal software engineer at ReturnPath, where he was leading the development of streaming data infrastructure and their data science platform. I won't take up any more of the time. Thank you to Davor and Ryan for being here today.
Thank you, Joanna, and Aaron as well. So I would like to talk a little bit today about machine learning. And I want to make the argument that the tools that we use to solve machine learning problems today were designed to solve the wrong problem. And as a result, these models can take months or even years to get into production. And I'm not talking about all machine learning models. I want to talk about a specific type today, and specifically machine learning models that deal with time, either that make predictions about the future or that are based on features that change over time. So as an example, we'll just kind of set out a trivial example. So imagine that you run a web page that serves videos to users, and you want to make a prediction about whether a particular user wants to watch Friends. And so this is our sort of trivial problem we're going to use to motivate our conversation. When a user begins a viewing session, we're going to predict if they want to watch Friends during that session, or if they will watch that. And you can imagine some simple features that you could build to use as the input to this model. So for example, you might want to ask, how many times has a given user watched comedies? So maybe the genre is predictive. Or you might want to ask, how many times have users the same age as a given user watched Friends? So maybe something about the user's age is predictive. And so we need to ask these questions in two fairly different contexts. First, we need to ask these questions to build a training data set. We need to build a large corpus of examples and use that to build a model from. And when we're doing this, we need to be able to produce examples relative to the point in time when the training example would have taken place. So our time is relative to that example. We need to have a large amount of historical data, and this operation is going to be optimized for throughput because we have a lot of data to process. Once we've trained this model and we're ready to put it into production, we have a different set of priorities and a slightly different problem to solve. In this case, we're going to be making predictions at the current time. And so all of our feature values are computed based on all the data that we have available generally. The most recent data is probably the most important. And so these systems are usually optimized for latency or freshness. And so I want to focus first on this training use case, because the problem with the training use case is that we actually need to ask a slightly different question than we started with. We need to ask how many times had a given user watched comedies at the time their session began. We need this example to be localized in time, to be contextual to a particular point in time. But it gets worse. This isn't the end of it, because we need to be able to ask this question at a large number of times. We need to be able to localize this computation to a number of different training examples, points and times. And so we're actually asking how many times had a given user watched comedies every time that they began a session. But we're still not done. It gets even more complex because we've just been talking about the feature. We also need to describe our target value. And in this particular case, we have one set of values or features that are computed when a user begins a session, but our target value, we can't know at that same point in time. We learn the target value at the end of their session. And so the target value needs to be computed at a different point in time. And so we need to be able to produce these two different values and then bring them together to produce a training example. And this is the complexity of building a training data set for models that are based on time. Once we've built our training set and trained our model, the production use case, we're back to our simple question. We just need to know how many times has a given user watched comedies, and we can compute that over all the data that we have available. And this is the problem that most of our tools are designed to solve. This is what I'm going to argue is the wrong problem to start with. But let's talk a little bit about how systems generally address this problem. Usually we do this by distributing the computation over some set of instances. This allows us to deal with larger data sets. And this is often done using associative and commutative aggregations. What we'll do here is we'll take our data, we'll break it into some number of partitions, we'll compute a partial aggregation over each partition, and then combine those together to give us the final answer. And this works really well. Let's say that we have some numbers and we want to aggregate. We'll compute the sum in this example. What we can do is we can compute a partial sum of half of these numbers in one place and the other half in another place. This gives us 9 and 11, and we can add those together to get our final value of 20. So looking at this as a sort of schematic, what we can see is that when we're in production and we want to answer these types of questions based on all the data we have available, breaking this up into partitions and using associative and commutative operations to compute these in more than one place and then bring them together is a great solution. And this works really well in production. But there's a hitch. And the hitch is that time isn't commutative. Order matters in time. And so when we're building training data sets, it's much harder to use this trick. It's much less efficient. So for the past 2 years, my team has been working on a different approach to this problem at Kaskada. And we take this from a different perspective. We start from a different kind of starting point, and it leads us to, I think, a really interesting new place. And it seems it's simple at first. We just process the data in order. We process it chronologically based on the time at which each event that we're processing occurred. So let's look at what this actually does in practice, what this means. So again, our goal here was to be able to produce a training data set. This is our focus right now. And we wanted to be able to produce a training data set where each value reflects a particular point in time. So we looked at how we can break this computation up using associative and commutative operations. But Kaskada uses a slightly different starting point for this. We start from this idea of a stateful aggregation. And this is basically just a function that has some state, and you merge in a value, and it produces a new state. So if we go back to that sum operation that we looked at just a second ago, in this case, we're doing the same operation effectively over the same set of values. But rather than breaking it up into smaller pieces, we're processing this one element at a time. And so at each point in time, we're producing a partial result, a result as of that point in time. We end up in the same place. In this case, we still produce the value of 20, but we now have a stream of results telling us how this sum changed over time as we processed more and more data. And so the data model that we use in Kaskada has this basic structure. We have both a value, for example, the number that we were adding up, and the time associated with that value. Every value in our data model includes this time component, and we process these values in chronological order, in the order that they occurred. And so what this means is that at every step along the way, every time we process a new value, we can produce a new output. We consume and produce streams of values. We can visualize this as sort of a step diagram, right? At each point along the way, we ingest some data and it produces a new value, but at any point in time, we can describe the current result. And so this is our foundation. This is where we're going to start from. So we've looked at this way of starting from stateful aggregations to produce a stream of point-in-time computation results. We looked at how we can use this to compute a number of examples. For example, that sum operation produced 5 different values with a single pass over the data. We only had to process that data set once. And we can use the single accumulator. In other words, we only had one sum value that we were using to compute those 5 results. We only need a single accumulator to store that value. And so this is an interesting starting point, hopefully. But there are some downsides here. So in a naive implementation, this seems to imply serialized execution, that we have to process every value that we know about, every event, one at a time in the order that they occurred. And obviously that's not great for being able to be performant and horizontally scalable. Another problem is that this seems to have a fixed time ordering. We've talked about this time value being part of each value that we process. And we're going to look at some ways in which there's value in being able to tweak that value a little bit and change the ordering. So I want to first take a look at how we can take on this first issue of serialized execution and recover some of the nice distribution properties of the associative and commutative approach. And then we're going to take a look at this time ordering problem, which we'll explain in a little more detail. But first, let's look at how we can distribute the computation. So again, our goal here is to be able to take this large set of values that we need to compute and somehow distribute it over more than one compute infrastructure. And so what we're going to do here, or what we've done at Kaskada, is we've introduced this idea of an entity to our data model. An entity is something like a user or a show. It's just some value that has meaning. And so to revise our data model a little bit, we talked about how every model or every value has a time associated with it. And so we also have added this idea of an entity. Every value is related to an entity. So let's try to make this a little bit more concrete. If we return to the feature that we were thinking about computing earlier, we said we wanted to predict how many times has a given user watched comedies. And so our process here is basically to partition each of the events in the data set by the user, because this feature is related to users. We were talking about how many times a given user has watched comedies. And then we're going to concurrently compute each partition's results. Now, within each partition, we have all the data associated with a particular entity, and each aggregation is scoped to an entity. So looking at the query language that we use, this is how you would describe this feature. We would say we want to count how many times a view by user genre equals comedy. And so this graph kind of shows 2 sample entities that we might want to be talking about here. We're looking at Alice, who has watched videos on our site 2 times. The first time she had seen 3 comedy videos, and the second time she had seen 4 comedy videos. Bob watched 2 videos as well and has a different value. And so this is sort of our first step towards making this process tractable computationally. It allows us to take the computation, break it up into smaller pieces, and distribute it across a cluster. But obviously, if we're going to provide this mechanism for breaking the computation up, we probably need to have a way to bring it back together. It would be nice if everything could be made embarrassingly parallel and split up like this, but in the real world, this usually is not possible. And so both to address this and to take advantage of some interesting features of chronological processing, we introduced this idea of point-in-time lookups. So let's look at our second feature to kind of explain what we mean by point-in-time lookups. We said we wanted to look at how many times have users the same age as a given user watched Friends. So the process that you would go through to do this would basically be these 3 steps. First, you'd want to determine how many times users of each age have watched Friends. In this case, we're talking about an entity of age. We're associating this computation with ages. Second, we would want to determine the age of each user each time they watch a video. So when a user watches a video, what is the age of that user? And then finally, we want to look up the value produced in the first step using the age determined in the second step. So we'll just run through how we do this in the query language. The first step this should look fairly similar. We're using a different table here. We're using a table named view by age. So each row in this table is associated with ages. It has an entity value of age rather than users. But this computes roughly a similar result as to what we started with. Looking at this graphically, here's an example of 3 different ages: 30-year-olds, 31-year-olds, and 40-year-olds. And we can see that they have aggregations that have a same kind of time value associated with each value. These things are changing over time as users of different ages watch videos on our platform. Our second step, we said that you wanted to be able to take each view event and figure out how old the user doing that was at the time. So this is fairly easy to do if we have some information about when each view event happened, in this case the year, and we have some user info about when each user was born. In this case, we can just subtract when the user was born from the year in which a video was watched, and that gives us their age. Now, there's an interesting thing to note here. In this case, our expression is combining 2 different data sources. On the left hand, we have view by user, which is effectively one table. And on the right hand, we have a separate table, which is this user info table. Notice we don't need to provide any join predicates here. We can just operate between them. This is because the entity key is our implicit join key. Anytime we want to operate between 2 expressions who have the same entity key, we can just work between them. And so this is a nice side effect of the data model that we've used here. If we look at the result of this computation, we can see that Alice, when she watched her first video, was 30 years old. And when she watched her second video, she had turned 31, because this happened much later in time. Bob, on the other hand, was 40 years old both times he watched a video. And we'll come back to this when we tie this all together, which is our next step. In this case, we've just assigned some names to these 2 computations that we looked at, and then we're going to use this lookup operation. So we said we want to take how many times each age has watched a movie and look up the particular age of each view event's user. And so this is how this would be described in our query language. So plotted graphically, here's what we can see. We can see that we are back to our original user entity, Alice and Bob. And there's 2 interesting things that we're showing here. We said that Alice was 30 years old when she watched the first video, but she was 31 years old when she watched the second. And you can see that the number of times that Friends has been watched is going down. This is because in the first case, we are looking up how many times 30-year-olds have watched Friends. And in the second case, we're looking up how many times 31-year-olds have watched Friends. So this is showing that as we move through time, the join predicate changes with time. Bob is showing another example, which is that Bob was 40 years old in both of these cases. However, over time, 40-year-olds watched more and more episodes of Friends. And so we can see that the result of his lookup is changing over time as well. And so what we're doing here is that we're allowing operations between different data sets in a way that preserves the point in time at which those operations are occurring. We're preserving this time axis. Obviously, if we're going to operate between values partitioned in different ways, we're going to need to introduce a shuffle operation. Our computations are broken into what we call passes. This allows us to do the first pass on data that's grouped or associated with users, for example, and the second pass over all the data that's associated with ages. In the first pass, we would compute the age of each user watching a video, and then that would be forwarded to the second pass, which has computed some information about each age. We think of these, we call these passes because they process data chronologically. Each pass potentially processes a different set of data, and there's a communication link between them in this case. Pass 1, as we said, was computing the age of each user, and then pass 2 was computing aggregations related to ages. And so just to kind of summarize where we are so far, we began by looking at how we could use this idea of an entity to distribute our computation across a cluster of processing compute nodes. We looked at how within each one of these partitions, we can process the data chronologically and retain some of the nice features of chronological processing. And then we looked at how this idea of doing point-in-time lookups across different data sources allows us to bridge the gap between different expressions, or different entities rather. So there's one thing I want to point out here, which is that in comparison to the sort of standard associative commutative approach to this problem, there are cases where we have to shuffle more data back and forth because we are not sending pre-aggregated partial aggregates. We're in some cases sending just streams of values. And so there is a downside to that. The benefits to that, again, is this ability to do point-in-time lookups. And there's a number of ways that we can give users the ability to trade off between this, which is beyond the depth of this particular conversation. And so this is kind of how we are able to take this seemingly inefficient computation of processing all of the values in the order they occurred one at a time and make it scalable and performant. So let's take a look now at how we want to handle time again. I kind of alluded to wanting to talk a little bit about ordering and relationships between values. And so I want to talk about what we call native time travel. And what we mean by this is time travel that is a part of the syntax of the queries that we're doing, time travel that is expressed in code. Our goal here, again, is to be able to compute different values at different points in time and then bring them together to produce training examples. We talked about how we need to compute both the features, for example, when a user begins a session, we want to compute their feature values, and later on their targets. So if we focus on the features, the basic process here that we want to go through is that we want to describe the feature expressions. So we looked at these. We looked at some graphs describing the two sort of example features that we wanted to compute. And then we're going to filter those features to just the points in time when a session is beginning for each user. So we can look at this as a table. We began with that graph that showed that we could compute these values at any point in time. And now we're going to filter to a specific set of times. These are the times when the session began. And we're going to just bring all of these features that we computed together into a record object here. And so if we look at Alice's first row, we can see that she's watched Friends 12 times at the 8:15. People her age had watched Friends 305 times, and she has watched 3 comedy genre shows. We'll come back to this. Notice the 8:15 point in time. But what we've done here is that we've applied this when filter. And what this is doing is it's saying, I am only interested in this feature's value at these specific points in time. Next, we said that we want to be able to compute the target values. We want to do that if they have watched Friends during a session. In other words, this needs to be computed at the end of the session. So our process here is to basically count how many times Friends was watched at the beginning of a session, shift that value forward in time to the end of the session, and compare it to how many times Friends has been watched at the end of the session. This time shift operation we'll talk a little bit more about, and this is one of the different features of our query language. So here's the result of this operation. So notice we began at 8:15 on Alice's first line, and now we're at 8:45. So this is when Alice's viewing session ended. So we took our features that we computed at the beginning of her session, we shifted them until the session end, and then we added a new value to this record. We added this target Boolean. We want to basically say that if the watches at the beginning of the session, input watches, is equal to watches at the end of the session, then if they're equal, I've confused myself already. If they're the same, then they have not watched anything. I think there's actually a bug in here. But in any case, this allows us to build the target value at a different point in time and describe the relationship between those two times using code, in this case, the shift until operation. So there's something to notice here, which is that because we're moving values forward in time, and because the values that we're using as the endpoint of the shift operation are based on data, different users may shift values a different duration into the future, and they may hop over each other. So what we've introduced here is not only the ability to change the values, the time values associated with the result of an operation, but potentially the ability to reorder the values within an operation. And so we accommodate this by introducing priority queues within these shift operations. Basically, as data is produced in one pass, it's written into a priority queue and then pulled out downstream as the second pass is ready to consume it. Now, there's an interesting optimization we can make here because values are only ever shifted forward in time. We don't allow values to shift backwards in time. That would represent information traveling from the future into the past, which is one of the guarantees that we want to be able to provide to users. And so what this means is that the second pass can pull values out of this queue anytime they are older than pass one. And so we only need to keep a queue that has this small section of the set of values produced. We don't have to produce all of the values from pass one and then sort them all in a single go. And so this is very useful for bounding the computational complexity of this sort operation. And so what we've looked at here is basically the ability to describe the temporal relationships between different values as code. And this allows us to compute training examples on demand without having to do backfills of new computations and snapshotting them. And there's a nice thing that we looked at here in this optimization where we can begin the computation of a pass before its upstream is completed because we know something about the ordering of that information. And so at this point, I think we've looked at how we can produce training examples using this approach of chronological processing. And so what I want to look at next is to briefly touch on how we can take queries produced in this kind of paradigm and put them into production. And this is going to really focus on being able to produce incremental query results. In production, we generally are interested in the current value, as we said. We want to know what is the result of a feature vector at the time of now. And so we want to be able to keep this as up to date as possible. We looked at how we do this in traditional systems, associative commutative. Some of these are able to use things like streaming or mini batches. And we take a somewhat similar approach. If we take a look at our fundamental operation, we begin by looking at this case where we have this function that has an internal state. It merges a value and produces a new state. And what you can notice here is that this state and a location in the stream fully describes the computation. In other words, if we know we're in the third element and we know the accumulator is 11, then we can just process forward from there, knowing nothing else about the previous values of this accumulator. And we take advantage of this to basically snapshot the state of these operations at the end of a computation. So in this graph, what we're showing on the horizontal axis is the time associated with each value, its occurrence time. And on the vertical axis, we're showing when that value was loaded into the system. So you can see in this case, we've loaded data in 2 batches occurring over different points in time. The red line is showing when a query occurred. We produced some results. And then we took the value of each of our accumulators that we had used to produce results, and we've written it out as a snapshot. What this allows us to do is, if that same query is made in the future, we can simply look to see if any data arrived since our snapshot was created. In this case, there's no data loaded inside this blue rectangle, and so we can use the results of the snapshot. We can say that there is no work to be done. Now, of course, this won't always be the case. Sometimes we'll get more data. And this is showing the kind of happy path. In this case, all of the data that's arrived since snapshot 1 was taken describes events that occurred after all of the events that are a part of the first snapshot. In this case, we can simply reload the values in snapshot 1, process all of these values that arrived in the third load event, and we have our new results. If this isn't the case, if data comes in that's delayed because there's latency in processing steps or the data just isn't on time for some reason, we can't use the second snapshot. This would violate our ordered processing guarantees. And so instead of using snapshot 2, what we'll do here is we'll go backwards in time to find the most recent snapshot that still manages to have this characteristic of all of the new data being inside this rectangle we described. In this case, we can load snapshot 1, and then instead of processing just the new events, we would process the 2 loads of events in this case. And so in this particular scenario, we have to process a little bit more data than would be ideal, but we still get to save some processing time. We don't have to process the first 2 data loads that we can see here. In practice, we find that this works pretty well because our data generally shows up in roughly chronological order. This is because the delays in the data are usually just processing delays. The events are still describing events roughly as they happen. And so it shows up more or less in this kind of top and to the right manner. So this approach to productionizing and incrementalizing computations is nice because it generally the cost of this operation generally scales with the throughput of the system. It has a nice feature in that at any point in time, we can load historical data. There are no bounds on how old the data can be. And there is no induced latency. We always give you the result of all of the data that's been ingested. On the downside to this approach, it's not ideal, it's not perfect. If the data that's being processed does not have this nice characteristic of being roughly ordered, we don't get as much improvement to the cost of the computations. Another downside potentially is that we have to store multiple snapshots to be able to look at different points in time as we move back to try to find a candidate snapshot. And this approach can have higher latency than a traditional streaming system. This is more of a mini batch approach than it is a pure streaming solution. But that's kind of how we approach the productionization use case. And it allows us to take feature vectors that were computed for this training case and do a pretty good job of serving them up to date in production. So let's recap where we've been. We started by looking at how it's difficult to compute training data sets using traditional associative commutative operations. And we introduced this idea of chronological processing. This approach to computing feature values reduces the computational complexity by reusing these accumulators and allowing you to produce examples as you move through your data set. It gives you query results that retain the history of the computation rather than just the final value after all the data has been processed. We looked at this idea of entities as a way of providing horizontal scalability through partitioning along entities. We looked at how this aspect of our data model allows for very concise join operations that you don't necessarily see because the entity can be used as the join predicate and the join key in most cases. And then when that doesn't work, we looked at how we have this idea of point-in-time lookups that allow operations between different entities while retaining the point-in-time nature of each result that we've computed. And finally, we looked at this idea of native time travel. This is the way that we can describe the temporal relationships between different values as code, and that this provides safety against time leakage by preventing values from being shifted backwards in time. And so this is the way that we think is a better way to build temporal machine learning models. We think that it's better to start with a system that can describe the temporal world and move into a world that is describing the point in time of right now. That this approach reduces the computational complexity of model training and results in substantially more expressive queries because it's better mapped to the way that we think about these problems. So we've built a product that is based on these ideas. It's free to try. You can see our sign up link here. I would love to get feedback on this. I'd love you to try it out and see how this works for you and see what the power of using a different approach to this is. And if these problems sound interesting to you, we're hiring. So I would love to talk to some of you guys, if so, in our booth afterwards, which again, we have a booth. So if you have any questions that don't get covered in the next 5 minutes, feel free to drop by. We would love to talk to you. So thank you very much.
Okay. Thank you, Ryan.
Yeah, thank you, Ryan.
Thanks.
We have a few questions in the chat, so we'll just get started. So in this new paradigm, how much does this speed up the time to production? Your initial graph showed 40% of models takes something like 7 to 12 months to get to product.
Yeah, so I don't have hard numbers to share on this, but I think that the real benefit here is that we're giving you tools that are based around the type of the production of the type of training data sets that you need. And so it avoids the need to kind of reverse engineer this in terms of systems that don't do this very well. In our kind of experience, this can bring the time down substantially because it's much easier to just describe the features that you're interested in. And you can iterate much more quickly, rather than having to traditionally, if we needed to compute some new type of aggregation, there would need to be a communication or a coordination between a data engineering platform and data science. That might take months just to build out the computation that needs to be done and start collecting data. Oftentimes, if what you're interested in collecting wasn't collected beforehand, you have to wait for the data to accumulate for a number of months. And because our system is based on the raw data, we start with the events that are just sort of as they happen. We can just produce those aggregations as a query expression effectively. And so all of that time goes away and you can just explore new things and try things out. So.
Thank you. There's a question that I think is or along that same line. So you mentioned that this is a different type of optimization. Can you give us an idea of how long it takes to compute 1 million or 10 million examples?
10 million examples, I believe, are somewhere in the order of 10 or 20 seconds, probably in most cases. I mean, it depends on the data you're dealing with and, you know, how it's partitioned, but our compute engine is highly optimized for processing data in kind of columnar batches. We use a couple of interesting technologies like Apache Arrow to kind of like really speed this up. We use like vectorization, which allows us to take advantage of like SIMD operations. And so our kind of like wall compute times are fairly quick, shall we say. So.
And it looks like this is the final question. What are some ML use cases where this temporal processing is needed?
Yeah, so I think we like to talk about three big ones. One is sort of personalization, where we're talking about we want to do a recommendation for a user that's specific to them. We want to know about what they've been doing over the past week or the past month. I want to make a recommendation just for them. And so personalization, I think, is one of the big use cases, and this is something that we were looking at in this case. Another case that we talk about a lot is sort of fraud detection. So when someone is doing a credit card transaction, we want to know about whether or not that vendor has been involved in a bunch of chargebacks recently, or has that user's behavior changed recently over time. And so in that case, I think it's a really good use case for that. And so these are the types of problems that we're really interested in focusing on, is either problems wherein the feature is changing over time, like it's specific to a user or something that's happening in the world, or we're making a prediction about the future. So for example, demand forecasting is another use case that we're interested in targeting, where we want to say, like, you know, how many rolls of toilet paper are we going to need to have on the shelves next month, right? Because these models have changed a lot recently. And so those are sort of like the main use cases of our system.
Okay, and so we're just about out of time. So I want to thank you, Ryan, again for your wonderful presentation. It was very clear and easy to follow. And thank you to our attendees for your questions. You can contact the speakers directly if you have any further questions or check out their booth. And please provide any feedback that you have using the form in the chat box. We're always looking to make things better. And thank you again, everyone, for joining us in this presentation, and enjoy the rest of your time in DataCon later.
Thank you.
See you.